Hello everyone, welcome to my presentation on channel equalization. Today I will explain why it is important for communication. We will learn how it helps fix problems like signal distortion and noise, making sure data gets through accurately. I will cover the basics and some more advanced stuff too. By the end, we will see how channel equalization makes communication better in different situations. Let's get started and explore this together. On this slide, we see two kinds of dots. Red ones for signals we send and blue ones for signals we receive. The red dots show that we want to send. They are either +1 or -1 here. But the blue dots show what actually arrives, and they are different from the red ones. This happens because the signals get messed up as they travel through the channel. The letters MOD, DEMOD, BPSK, and BER helps us understand how signals are processed. They tell us about things like how we change the signals, how we get them back, what kind of change we make, and how many mistakes happen. Channel equalization is really important here. It helps fix the mess in the signals and makes sure they are more like what we wanted to send. By doing this, we can make communication more reliable and accurate. So, learning about channel equalization is key to making communication work better. Let's talk about the terminologies. When we send signals through a channel, sometimes the channel can get mixed up with each other, especially if they are close together in time. We call this mixing up intersymbol interference, represented by ISI. Intersymbol interference is a big problem for wireless communication because it can make our signals hard to understand. Equalization is a way to fix this problem. It's like cleaning up the mess the channel makes with our signals, so they are easier to understand. By using equalization, we can get rid of intersymbol interference and make our communication system work better. Let me talk about terminologies here again. For the power delay profile, this shows us how strong the signal is at different times because of delays in the channel. It helps us understand how the signal changes over time due to channel's characteristics. Mean access delay, this tells us on average how much longer the signal takes to arrive after its initial delay. It's like the average extra waiting time for the signal. To talk about mean square access delay, this is the average of the square of the delays after the initial delay. It helps us understand the spread of delays more accurately. RMS delay spread measures how much the delay times vary. It's like telling us how spread out or varied the delays are. Channel coherence bandwidth, which is called BC, this tells us how much the channel stays the same across different frequencies. It helps us understand the range of frequencies over which the channel behaves similarly. I need to talk about flat fading in this regard. Flat fading channel is the frequency selective fading channel. In a flat fading channel, the coherence bandwidth is bigger than the signal bandwidth BS, meaning the channel doesn't change much across the frequencies used. In contrast, in a frequency selective fading channel, the coherence bandwidth is smaller, indicating that the channel changes a lot across different frequencies. Lastly, I would like to talk about the intersymbol interference, which is ISI. This happens when symbols in the signal overlap because of the channel, causing confusion or errors in decoding the message. It's like when words get jumbled up in a sentence because of noise or interference. Here, important documentation that we can calculate them. I need to say some notes that are important. Pi in these equations must be in decimal values. If they are given in dB, you must convert them to decimal values before calculation. Let's have an example and understand better. As you see the figure, given a channel with a power delay profile in figure, calculate the mean access delay, mean square access delay, RMS delay spread, and the coherent bandwidth of the channel if it is estimated by the formula. Would this channel be suitable for GSM service, which requires a total bandwidth of 200 kHz without the use of an equalizer? So in this regard, we need to use these formulations to answer this question. So to solve this question, convert decimal values, dB values to decimal values first. After that, put each values to the mean axis delay to calculate mean axis delay. It is the average value of the axis delay values weighted by the corresponding multipath powers. And then calculate the mean square axis delay, which is the square axis delay values weighted by the corresponding multipath powers. After that, we gonna calculate the RMS delay spread, which is the statistical measure of how far the real delay may vary around the mean axis delay, and it is calculated as shown in slide. And finally, we need to calculate the coherence bandwidth using the RMS delay spread. And our result is 146 kHz. Let's illustrate the intersymbol interference in frequency domain. If Bs greater than Bc, channel is called frequency selective fading channel. So therefore, ISI exists. And spectrum of received signal is distorted in this situation. But if Bs less than Bc, channel is called flat fading channel. And that's why there is no ISI. Both attitude you can see in slide. To sum up the solution of this question, GSM service requires a total of bandwidth of 200 kHz, which exceeds the above channel coherence bandwidth. In other words, the given channel is a frequency selective fading channel for the GSM signal. This effect causes the intersymbol interference for the transmitted GSM signal, and as a result, the transmitted signal might not be correctly covered. In the frequency domain, the spectrum of the transmitted GSM signal will be distorted. To transmit the signal through a band-limited frequency selective fading channel like this case, in addition to a digital modulation scheme such as PSK and QAM, a channel equalizer need to be used. This is the formulation of ISI that we use linear convolution between the two vector x and c, and we find y. Let's continue the formulation. We know that if D equals A convolution B, then the n element of D is denoted as Dn equals the sum of Am dot times Bn n minus m. Hence, the received signal at the arbitrary time instance and at the receiver is shown below. And Inter's ISI value is denoted as in this formulation like that. This means received signals include signal of interest xn plus its ghost version, and ghost version is called ISI. Here, channel equalization eliminates the effect of channel. If frequency selective fading exists, it is needed to mitigate ISI. If flat fading happens, it just simply mitigates the amplitude and phase distortion caused by channel. So, equalization concept tries to reverse the impact of channel, for example by using an equalizer that inverses the channel frequency response. Here is an example of a FAR filter. This filter has an order of P. Let's talk about the equalization concept in frequency selective fading. Channel can be modeled as a FAR filter, a filter having feed-forward paths only, and our task is to construct another FAR filter to inverse the channel frequency response. Cascading the channel and the equalizer will eliminate the inter-system interference in our signal. In this regard, there is one question. The question is, can I change the order of these two blocks? Yes, you can change the order. You can put this equalizer in front of the channel as well. That's all, guys. Thank you for listening to me. Please subscribe my channel.